Let's get going. We're going to be talking about some more items in Chapter 4, the symmetries of space-time, and the new concept that we're going to work on today is energy. But before we do that, we're going to do some stopping time practice in the form of iClicker questions. So turn your clickers on. And just to reinforce, here's the SI schedule. So we've already had SI today. Did you have anybody come?
No one came today.
What? Nobody came?
Yeah, I was about to take a nap, but I am.
Well, I think on Monday you'll have some students because we're going to have some homework this weekend. I know that'll cheer everybody up. Plenty of homework. Anyways, let's get going. We're going to work at an example in class now from an old homework assignment that I dug up, and you'll see it's from another semester. Here's the basic setup. These two weird polygons, one is kind of a Pac-Man shaped, what is that? That's a sevenagon, and then the other one's a green triangle. I call the green triangle the delta molecule, and the yellow one the H molecule. Now these are, that's not really what molecules like, but molecules do interact, and so we're going to study this one now. One of them, they each have an integral multiple of the mass unit, what I call the molecular mass unit. So let's say we're going to say that the green delta molecule over here has exactly one molecular mass unit. Now we're going to use that as if it were a kilogram. All right, molecules are definitely not that big. They're much, much smaller in mass than a kilogram. But let's say that the yellow H molecule, they're going to jam together. You can see the green one's coming in like a freight train from the left, and it's going to interact and collide with the yellow molecule, 5 molecular mass units. Okay, so go ahead and write that down as well. And you can't see it here, but the initial speed of the delta molecule is 12.3 meters per second. And the yellow one is at rest. So write down that as well. Matter of fact, here's the first problem. All right, the initial speed. Let me start it. Hold on. Look at that. Clicker back over here. The initial speed of the delta molecule is 12.3 meters per second, and it's 1 molecular mass unit. What is the momentum of the delta molecule in MMU meters per second? So think of that as if it were kilogram meters per second. Instead of kilograms, we're using molecular mass units. So what would the momentum be? This is A, B, C, or D. Remember the definition, the definition of momentum? P equals what times what? Right, mass times velocity. All right, so you can figure that out. "30 seconds to vote, starting now. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, let's see what you guys voted for. Yeah, pretty good. This is the right answer. C. And yeah. So now let's follow up with this next question. All right. The initial speed of the delta molecule is 12.3, as before. What is the momentum of the entire hex molecule, which is the combination of the yellow and the green into kind of a yellowish green hexagonal molecule? So what is the momentum of that molecule in molecular mass units, molecular mass unit meters per second after the interaction, i.e. after the delta molecule sticks to H? So while you're thinking it over, just, feel free to talk to your neighbor and, kind of, or if your neighbor is the TA or the SI, feel free to talk to them. 30 seconds to vote. Don't forget to vote. Yeah. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for here. Looks pretty good. The correct answer is C. And now let me ask you this. This is not on the screen. It's not a question, formal question, but um, uh, why is this true? How would you answer that question? Why is this true? You're in a court of scientific law, and the judge is Professor Galileo, and Professor Galileo says, "My student, you must justify that. What is the scientific reason that that is the momentum?" What would you tell Professor Galileo? Or Dr. Judge, Your Honor, Galileo? Raise your hand if you want to volunteer an answer. Uh, okay, you. I saw you first. What's that? The exchange of what is equal? Huh? No, speeds don't get exchanged. What would you, that's good, that's a good part answer. Okay, on the aisle. Yeah, you. Yeah. Oh, what? I couldn't hear you. Did I said C? Oh my goodness. Let me go back to that. Uh, I messed up. Hold on. Let me go back to this. Oh my goodness. Uh, it's B is right. B is. Why is B correct? I'm sorry. I'm sorry for misleading everybody about that. I clicked the wrong number. B is correct. 12.3 molecular mass unit meters per second. Why is that correct? Why is it? Okay, back there. Ding! Conservation of momentum. Okay, which is now you guys over here. It's an exchange of momentum that's equal. All right. So sorry I messed that up for you guys. Oh, I know what that 73 point, that's 6 times 12, right? Ooh, don't, good. I'm glad I went over that with you guys. And in fact, I almost got caught napping on that. Okay. So I'm going to have to change this. I'll modify this just a little bit before we put it on YouTube. So now let's try a combination of velocity graph and impulse equation, which we just used, to get a stopping distance. All right. Now remember, I told you that the two main tasks that we have are to figure out a stopping distance or use a stopping distance, and number two, figure out a stopping time or use a stopping time. Okay, so this is a little bit new information, and so let's do this, and hopefully you won't be forcing Godzilla into a facepalm of epic magnitude. So here's the problem. And this is from another old homework assignment. You can tell it looks like a homework assignment. And this one's a brain burner. And in fact, I think did we use this little kid at the ice skating rink before? Okay. You observe and video a little kid take a spill and slide at the rink. Um, he slides to a stop. By analyzing the video on your cell phone, you know that the little kid's mass is 30 kilograms, and his initial speed was 3.4 meters per second. Furthermore, your uncle runs the rink, so you know the friction force F on the little kid. F equals negative 19.2 newtons. So that's leftward newtons in our sketch. So here's the data. Make a note of that. Okay. And then here's the, so 30 kilograms for the mass of this little shrimpy kid. And then 3.4 meters per second for his speed. So that's about 7 miles an hour, something like that. So he's not really booking, but he thinks he is. And he takes a spill, and he slides. And we're trying to figure out the distance that it takes for him to stop under this frictional amount of frictional force. Okay? And your uncle runs the rink, so he knows how it works. All right? So now, comment number one, we have enough information to figure out a stopping time using F delta T equals delta P. But what we want to figure, that's nice, but we want to figure out a stopping distance, right? And so what we're going to do is use a velocity graph, because we can also make a velocity graph for this shrimpy little kid. He started at 3.4, comes to a stop, right? That's a triangle on a velocity graph. And we know his initial speed, so we can figure everything out. We know how long it takes him to stop. All right, so here we go. So here's a velocity graph of the little kid coming to rest. So the upper part of the triangle is at positive 3.4 meters per second. Okay, that was from the setup of the problem. All right, that sounds good. All right, now the other end of the triangle is delta T, the stopping time. Now we haven't got that yet, but we can do the impulse formula and get it. All right, that's what we're going to do now. All right, so we're using the impulse formula to set up a velocity graph and then do good old 1/2 base times height. So if we can get the stopping time delta T, we'll get the stopping distance. That's the area of that triangle, the distance triangle. All right. So here's the good old impulse equation. F delta T equals delta P. All right. So and I'm going to drop the minus signs now because we know what the size of all the magnitudes are. The force, the frictional force, 19.2 newtons. All right. Now, what's 30 kilograms times 3.4 meters per second? Oh, wait a minute. Did I say 60 kilograms for the little kid? I said 30? Okay. All right. So 30, so that's what, 90 or 100 or so? 102 exactly? Okay. All right. So 102, yeah. Okay. 102 kilogram meters. All right, so that's how much he's lost. All right, so if we put in the minus signs, we'd have a negative 19.2 newtons and a negative 102. And then they cancel out, so we'd be left with where we are right now. So, all right, so now how do you get delta T by itself? Yeah, okay, divide like this. Okay, divide both sides by 19.2, and you get delta T by itself. And then over here on the right, you get 5.3125. Better verify that. Is that right? 102 over 19. Yeah, that's about right. You know how I mentally estimate this? This might help you on a test. 102 is close to 100. 19.2 is close to 20. So this is close, Caitlin, to 100 over 20. And that's easy to do in your head. 100 over 20, that's just 5. So my answer better be 5 point something, which it is. And then you go to your calculator, and yep, it is 5.1. It's a little bit bigger than 5, or 5.3125. All right, so now we have delta T. We've got the top of the triangle. We've got the right side of the triangle figured out. That's going to be 5.3 over there. All right. You guys got a question back there? You just, I mean, or you're talking about this, or rather than just what? But we're about to use that. Yeah. Can you see it? Yeah. I had, you guys had to look like, yeah, I see what he's doing now. Good. When you can be one step ahead of Dr. B, that's where you want to be. But it's hard to do it. I got to stay one step ahead of you guys. That's why they pay me the big bucks. All right, so here's the area of a rectangle, 5.3125 times 3.4, and then for the triangle, we want to divide that by 2. All right, so that's 18.0625 divided by 2. So that's like 9.03 something. And if you look at the problem, this one to the nearest meter, no, to the nearest tenth of a meter is, let's go back here. Let's do all this stuff. Okay, so to the nearest tenth of a meter, 18.0625 divided by 2 is 9.03. So to the nearest tenth of a meter, this would be 9.0. And that's what we get. So when you do this correct, you get 2 points on that old homework. All right. So that's just a little bit of a reinforcement. Now, let me just pause at this point and remind you that there's the two classic dynamical calculations that we want to be able to do are stopping time and stopping distance. Now, we just did a stopping distance by first figuring out a stopping time. There's an easy way to do it with just one move, and that's using energy. And that's what we're going to try to tackle today, stopping distance and stopping energy. But before we do that, I want to talk about this concept of recoil. Now, this is an M1 Abrams tank, and when it fires that projectile, you do not want to be standing directly in front of that projectile, man. That's gonna take out any Russian tank that they got or any other tank. All right, but it's going to cause this big monster tank to recoil backwards. Now it's a big machine, and that's not a very big projectile, so it's not going to rock back a whole lot. But they'll notice it because it's really jamming. It's really fast. Look at those flames blazing out of there. So that means that they've really put a lot of velocity onto that small projectile. So the Abrams is going to rock back a little bit, noticeably. Did you ever ride in one? 120 millimeters. So that's about 4 what would that be about? Almost 5 inches. Okay. So maybe about this big around. all right, and it'll kill anything. And so they really got to, but they want it to get downrange fast. They want to get it right now, and that momentum in the projectile is actually part of what kills the enemy tank. You know, just the momentum of something really fast, even though it's small, can knock something out, even if it doesn't have an explosive. But this one, I don't know what kind this one is. Some of them, that's all they do. They don't have an explosive. They just have a big chunk of uranium, very high density metal, and it basically melts its way through the shell of the other tank because it's so hot by the time it strikes the tank. So anyways, let's talk about recoil. Whatever momentum, whatever delta P is exchanged by the bullet or the projectile, the rifle or the tank gets the same amount, but in the opposite direction. So if your tank round is going off to the right with a certain amount of momentum, the recoil momentum on the tank is going to be the same amount of momentum, but off in this direction. Okay, so that's the exchange. And guess what? That's just like skateboarders exchanging, doing the patty cake when we had Caitlin and Joyce doing that. It's the exact same thing. All right. Except the tank projectile is much smaller. So it would be like Joyce, a regular sized student like Joyce or Caitlin, doing patty cake with an ant. So if that were possible, because they have a lot of mass compared to, I mean, they're both approximately the same mass, roughly, you know, but but a tank and the tank round are definitely not the same mass. So think of it as Caitlin or Joyce versus an ant, or versus even an apple, something really small, and that's what the tank is. So in the barrel of the gun, it's here. This is where it is. It's loaded right now. So I've symbolized by this black sphere. All right, and by the time it gets out the end of the gun barrel, it's not going to get much pushback. All right, the propellant is mostly going to dissipate once you get out there. So by the time it gets out there, you get this big explosion and it forces the projectile out. But then once it's out, turn around, get a projectile view here. Okay, once it's out here, it's pretty much finished speeding up. All right, maybe a little bit, but so anyways, we got an interaction distance. All right, and the rifle or the tank gets a little bit of delta X off in this direction. All right, it gets a little bit of rocking, and so the size of that recoil, if you're shooting a hunting rifle, and it'll give you a little kick in the shoulder, depending on some of these big sniper rifles they have really big bullets and a really long barrel, and they put out a lot of momentum into that bullet, and they can shoot a target, like a mile away. Some of those guys, all right, and they have the special padding on the sniper rifle on the stock so that it doesn't totally dislocate the shoulder of the guy that's holding it. So you're holding this rifle, and you'll get a little kickback. The only rifle I ever shot was at summer camp, little 22 rifles for riflery practice. But even those, you'll get a little kick. Right? A shotgun will give you a lot of kick. It just depends on the bullet and the rifle and stuff like that. Now, let's work out a problem here. All right. This is from, guess what? Another homework from the olden days. I think I'm going to give you this one again, a different version. A rifle of go ahead and make notes. A rifle of slightly more mass, M subscript R, 1.50 kilograms, fires a bullet to the right. Okay, so the bullet's going this way. The rifle's going to be going this way. All right, but they're exchanging momentum. And the rifle, or the bullet, has a speed of 206 meters per second. Now that's actually that's not very fast for a bullet, but we'll just pretend it's only about 450 miles an hour, which is pretty fast for most things, but for a bullet, I don't think it's that fast. Anyway, so the mass of the bullet is pretty small, 0.025 kilograms. So that's 25 grams. That's about the mass of a, what do you call it? A quarter, I think, is about that much. Okay, so it's not a very big bullet. It doesn't have a very big speed. But the size of the rifle recoil momentum is the same as whatever the bullet gets. So figure out what the bullet's getting over here, and then the same size momentum off to the left for the rifle. All right. So the rifle's going to absorb a bunch of momentum. So and what we're going to do is just work on the size of the rifle's momentum. So we're not going to. We know which direction it is. It's to the left. So now we just want to get how big it is. All right. So let me park this image off to the right and let's work it out. Okay. The momentum of the bullet, it goes from zip zap to about 7.125 kilogram meters per second. And that's because, oh my goodness, this is not using 206, this is using 285. All right, so take that into account. I used what this is, it's because every time you do one of these calculation problems in web courses, they give you a different random number. So cross out the initial speed that we had before. I think it was, what was it, 206? And pencil in 285. All right. And so the mass of the bullet is still the same, 0.025 kilograms. And so its initial speed, 285. So that's how much momentum it has absorbed from the rifle. And so the rifle has whatever that is except the opposite direction. So negative 7.125 kilogram meters per second. All right. And so that'll give the rifle a little bit of kick off to the left. You know, the bullet's going over this way, and the rifle kick is into your shoulder. You know, you're shooting in that direction, and the rifle kick is back into your shoulder, so back this way. And that's what recoil is. Now, in this assignment, it was just the size that we were after. And I think I put down to the nearest tenth of a kilogram meter per second. So this is the actual answer. Okay, and the reason is because we know the direction. Students, whenever I ask you for the size of something, I'm always going to ask, that means type in a positive number, you know, whatever it works out to be. All right. So I might say, what's the speed of something? That's always a positive number. A velocity might be positive 22 meters per second or negative 22 meters per second. But a speed is always a positive, like the numbers on your speedometer. They're always positive, no matter what direction you're going. Same thing here. So, and the reason I do this is because on iClickers, it's easy to answer numbers or letters, but not the combinations of both. So this makes it a little bit simpler to use the iClicker. All right. So that's that problem. Right now, so this weekend, when you have some homework, you know, you might find this calculation handy, and I'll try to get this lecture YouTubed up as soon as I can after I get home. Are you okay? Are you feeling all right? No, you in the aisle seat with the white collar. You doing okay? This is just making. She was sitting over there with this kind of look of pain, and I guess it's because of all these equations and stuff. Kind of, okay, well, that explains it. We're just hanging in there. We're doing all right. We're going to be good. We're going to be good. Yeah. Impulse formula. F delta T equals delta P. Yeah. Well, no, we're just, you know, on this one, let me go back here. On this one, we're just asking about the recoil momentum. So all you got to think of is, you know, what's the change in the momentum? In other words, we're not, in fact, it's difficult to do the force here. the projectile force on the bullet. So think of it this way: we're just doing the right-hand side of the equation, and we're given enough information to figure it out. All right. So with this, if I told you that it was in the rifle barrel for 0.021 seconds, then you could figure out the push force, the average push force out of the rifle, pushing on the bullet. But so if I just ask delta P, that's just the right side of that impulse equation. All right, so let's keep going. Come on, here we go. All right, now last time we talked about space-time and the symmetries of space-time. And I ended with this question: what does it mean when we claim that our world is a four-dimensional space-time? And that's what Albert Einstein is famous for establishing. That it's not just three directions, x-axis, y-axis out towards you guys, and z-axis vertically towards the sky. But the time is a fourth dimension, and you have to treat it on an equal footing with a spatial dimension. And I'm going to show you how to do that. And he also said that momentum and energy are the dynamical quantities that go with the geometric quantities of space and time. So in the four-dimensional view of the universe, there's three spatial dimensions, x, y, and z, and one temporal dimension, time, all right? And it gets really interesting when you try to figure out curved space-time. But we're just doing flat, normal space-time like what we have here on Earth. All right, so here are the three spatial dimensions, as I mentioned. X go in one direction and perpendicular to that, Y, and then perpendicular to both the Z-axis. So like if the lectern, actually this is kind of turned around from what I described a few minutes ago. So this one, the Y-axis is going out here in this direction, and the X-axis is going out towards you guys, and the Z-axis is going straight up. So that's all right. That's a good X, Y, Z axis situation. All right, and it's just a we're not going to make any calculations off this, but something to show you spatially what we mean by that. Now, the dynamical quantities that encode interaction and potential for interaction. Make sure you write that: encode interaction and potential for interaction. Are momentum and momentum is a mass times a spatial velocity, so P equals mv. And the other quantity is energy. And an example of that is a famous Einstein equation, E equals mc squared. Everybody's seen that, or almost everybody. And there's many other forms of energy that you can write. And what Einstein said is, all right, if you think of our universe as three spatial dimensions and time as the fourth dimension, then it makes sense to also use energy and three spatial momentum components as your physical dynamical quantity that you study. And so I've already told you, and the spatial momentum part is affected by impulse. The energy part is also going to be affected by forces, and I'm going to show you how that works today. So here we are back to this three-dimensional diagram. And so here are the three spatial components, and we use a subscript to denote which direction. So if we have, so if this is the x direction, and you're moving only along this direction, then px would be, like 5.2 kilogram meters per second, and then py out towards you would be 0, and pz would be 0. But if you're kind of tilted out, a little bit of x, a little bit of y, a little bit of z, this is how you'd have three different numbers in there. All right, and then you have to use the Pythagorean theorem to figure out the total velocity, if you're, and so that's pretty easy to do too. But we're not going to mess around with that too much. Right now, coordinates and dimensions in space-time. So let's talk some more about that. We construct and I'm going to show you how to make a space-time diagram. We construct a coordinate system in order to diagram and calculate. We've done that before, distances, curves, all kinds of stuff. And we use it to mark various events. In other words, starting and stopping events. Dropping something from the top of the library and landing on the sidewalk below you. All kinds of different events. Okay, and so usually the rectangular coordinate system X, Y, and Z is what we use, but it could be a spherical or other curvilinear coordinate system. A spherical coordinate system is like latitude and longitude on the surface of the Earth. And then the third coordinate there would be R, the radial distance from the center of the Earth. Okay, so when NASA is charting out the position of a satellite, they might go latitude and longitude and then altitude, how far away from the surface of the Earth. Okay, so that's a spherical coordinate system. And then curvilinear coordinate system would be like not a spherical, but an elliptical or ellipsoidal coordinate system, which you might use if you're orbiting some irregular shaped asteroid or something. And we've had spacecraft orbiting. I think we've had one or two now, maybe a few more spacecraft that have orbited asteroids. And we've landed one of our spacecraft on an asteroid, the Eros satellite, about 20 years ago. Now, Einstein says that we have to use time as more than a bookkeeping tool. A bookkeeping tool, everybody uses them. You look at your bank statement from the bank online, and every debit that you put on your card, it's got a time and a date, which is good. That's one way you can tell if it's a righteous debit or not. And then, so that's, your checking account. What else? Newspaper. You buy the newspaper. It's always got the time. Homework. You turn in it's kind of old timey now, but turning in a homework paper, your teacher usually, they want you to put your name on it, and it's got to be by a certain date. All right. But, so you can think of it that way as something for calendars and checkbooks, but you have to be, if you want to consider it as a true spatial dimension, it's going to be forces you to do things a little bit differently, and that's what Einstein said in the Grand Book of the Universe. He said you've got to think of this grand universe of ours as four-dimensional. So you have to figure out how to handle time as one of the four dimensions. All right. So in some way you have to treat time as if it were an XY coordinate as much as possible. All right. Now here's another thing that we mentioned last time, and that's the position and the energy momentum vectors. Now, this is a fancy way of expressing, X, Y, Z coordinates in a column vector like that. And notice in the very first one, it's time. All right. And that's a column vector in space-time giving the position and the time of a certain event. All right. So the moment that you release the water balloon, that has a fixed position in X, Y, Z, and in time, the moment you drop it. And then when it hits the sidewalk, it has another time, just a second later or so, and then X, Y, and Z positions as well, right? And if you throw the water balloon, the same thing. The moment it leaves your hand, and then arcs up into the sky, and then all the way down the sidewalk over there far away, that's another time and position, right? Now over on the energy momentum side, that's a four-dimensional vector. And energy is in the very first slot. So energy corresponds to time. and momentum corresponds to space. And we're going to see how the formulas that even Sir Isaac Newton, well, not Sir Isaac Newton, but maybe guys a little bit after Sir Isaac Newton, all their formulas had this stuff encoded in it. They just didn't see it. All right, so let's make a simple space-time graph now. All right, now this is going to be making, it's going to look like graph paper, but it's going to have a special meaning. All right, now to make this vertical axis, that's going to be our temporal axis. To make it measured in meters, we're actually going to label it the CT axis. So speed of light c times time. All right. So that's like measuring time in light years. You know, light years is a unit of distance. The speed of light times an amount of time, 1 year. Okay. So the CT axis, the vertical CT axis, is like light years. Okay. And then the x-axis is, and here's the CT axis. And the x-axis is going to be, you know, just same old light. That'll be meters or light years or anything else, right? So this is how we make a space-time axis or a space-time graph. Now, let's put in a horizontal line, set of horizontal lines up here in the first quadrant, all right? And the distance between each, let's say that the distance between each line is c delta t. You know, so that could be a light second, for instance. You know, the speed of light times 1. Do you know how far the Earth is from the sun? It's 500 light seconds. It takes light from the sun 500 seconds to get to Earth. So we say that the distance is pretty close to exactly 500 light seconds. So that's like 8 minutes and 20 seconds to get from the sun to Earth. Okay. So that's what we're doing. So c delta t, you can think of that as light seconds. All right. Now, if you think about the impulse equation, here's what the impulse equation looks like. All right. Now it's got delta t's. It doesn't have any c's in there. Okay. So we're going to overlook that for the moment. But it does have a delta t on the left, and it has a force on the left. And we know that those are equal when you're doing some kind of a skateboard interaction, some kind of a recoil interaction, some kind of a collision. You know, there's going to be some F delta T. And we know that that corresponds to a change in the momentum. Now, here's the interesting thing. On the left is a force and a time. On the right is a momentum. And that's significant because the momentum is a spatial momentum. All right? So we have this kind of curious business here where you have a spatial, the dynamical quantity that corresponds four-dimensionally to the spatial coordinates. But over here, you have the temporal coordinate. You have a delta t. Now, this is the impulse equation of Sir Isaac Newton. It was staring at him the whole time. But nobody figured it out until Einstein. All right? So that's the horizontal. So for the horizontal partition, or the horizontal lines of partition like that, the graph paper lines that go horizontally, they're all c delta t's. There is a dynamical equation, the impulse equation. Now let's do some partitioning of space-time in the vertical manner. Okay, so let's put in a bunch of, try to make them square, you know, like graph paper is. All right, so these are delta x's. You know, delta x, another delta x, another delta x, another delta x. All right. Now remember, the impulse equation is completely understandable in terms of delta t's. So the question now is, how does nature behave under this partition? In other words, with delta x's, what kind of law shapes nature's motions using delta x's? I mean, for delta t's, we got the impulse equation, and we've used it several times. Is there something for delta x? And the answer to that is, yes, there is. It's called kinetic energy and work. And there, my wonderful students, is the work formula. F delta X, that's the work. Just like F delta T is the impulse. That's equal to the change in the kinetic energy. All right? Kinetic energy is defined as 1/2 mv squared. Now, let's think about this for a second. If something is speeding up, that means its v is increasing to the right, its momentum is increasing to the right, and its kinetic energy, it's 1/2 mv squared, increasing to the right. Now, the thing about it is, though, the v in the v squared there is the total velocity. So that's a speedometer reading, no matter what. This one's directionless. There's no direction in the mv squared, 1/2 mv squared. So you could have the same mass and go 5 meters per second in any direction, and you still have the same amount of kinetic energy, right? And that's I don't think anybody really knows why that is. You know, why isn't it 1/2 mv to the third power? Or 1/3 mv to the third power? Or 2.5 times mv to the 19th power, or any other power? Why is it 1/2 mv squared? I don't think anybody knows. I mean, we know the math of it, but why nature arranged itself that way is kind of a profound riddle. But this is the formula that goes with the delta x's, the work formula, right? So F delta x equals delta KE. That's the work formula. And then you got to, and just like with the impulse formula, you got to remember the definition of the stuff on the right, delta KE in this case. So you got to remember, just like with impulse, delta P, you have to remember, okay, P is equal to mv, right? For this one, delta KE, you got to remember that kinetic energy is 1/2 mv squared, right? So let's take a look at this. Let's take a look at some simple calculations. For instance, the metric unit of work is called the joule, right? Now this one does have a special name for a scientist from England called William Prescott Joule, I think his name is. James Prescott Joule. I think that's it. And it's 1.00 kilogram meter squared per second squared. And it has the same units as kinetic energy. So for instance, if you're going if you have a 1 kilogram mass and it's moving off to any direction at 1.00 meters per second on the speedometer, the kinetic energy is 0.5 times 1 times 1 squared. And so that works out to 0.5 kilogram meter squared per second squared. And that's the same as a joule. All right. Now that's just the definition, and that's half a joule. Okay. A full joule is just one of those. All right. So now let's take a look at the work part of it. Okay. The F delta X part of it. All right. Say that you have a 1 Newton force. So you have some, a little tiny force from a little, a little kid or any kind of force that you can, and it moves something through a distance of 1.00 meters. So it moves its position and it forces something to speed up, and over 1 meter of distance, this is how much work it does, 1.00 joules. Now, it's also the same as a Newton meter, Nm. All right? And so the joule, in its most fundamental units, is kilogram meter squared per second squared. Sometimes it's helpful to use 1.00 Newton meters, and they're equivalent. Okay, so you could write down joule, capital J, or you could write kilogram meter squared per second squared, or you could write Newton meter. All three of those are the same. All right, and that's the metric unit of work, or one of the metric units of work. The other one is the calorie. So if you look at your nutrition facts on your bag of Cheetos or whatever you're having for lunch, it always has calories on the back. So that's a unit of energy. For us, that's food energy. Now, I'm loading you up with a lot of concepts here. Let me pause here for questions. I see a few people kind of grimacing and stuff. Ask a question if you have one. Okay, let's keep going. Here's another important quantity, important with interactions, and that's called potential energy. All right. So, an example of that is a baseball. So you take a baseball, and when it rises, it loses kinetic energy. But if it lands, up on exactly on top of the wall at the stadium, or exactly up on top of a windowsill, and you throw it from the street and it lands straight up there, it still has the potential to acquire kinetic energy on the way back down. So we define gravitational potential energy in this way. The opposite of the work, F delta X. So gravitational potential energy is minus F delta. In fact, it's minus F delta Y if you think of the the vertical coordinates. So if something's coming straight down or arcing down, the potential energy relies on the height above the floor, or the height above sea level, or the height above the top of your house, or the top of the library, or whatever you're working on. All right. And so the weight force, we already know, mg, with a minus sign in there, in the value of g. So what that means is that for the baseball, the gravitational potential energy is minus mg delta y. Actually, that should be delta GPE. I think I'll try to change that after class. Minus delta GPE is minus mg delta y. All right. And that's following the idea of that it's the opposite of the work. Okay. So if you think of the energy this way, then any kind of a ballistic arc or any other gravitational trajectory you can think of as an exchange, but not an exchange of momentum, but an exchange of energies. So if you partition your delta x's, that gives you leverage on your delta y's, or that gives you leverage to think of everything as an exchange of energy. And that's sometimes a lovely way to look at it. And Einstein says you got to look at it in both ways. The delta t, the horizontal lines for the impulse formula, for the sideways lines, the work formula. And it works really nicely. So every joule of kinetic energy that you lose on the way up as the baseball slows down, it goes into a joule of potential energy. You can think of it as stored energy, stored in the baseball, and given to the baseball by the motion. Vice versa, a joule of potential energy lost on the way down. So if you think of this as a losing GPE on the way, that's what happens on the way down. And what happens to it? It goes straight into kinetic. That's what happens. When something falls, you gain more speed. In fact, you gain more 1/2 mv squared. And if you calculate gravitational potential energy minus mgy, then the v squared that you gain, the 1/2 mv squared, is exactly the same as what they exactly balance each other. All right. The total energy, therefore, is exactly constant. Now, this is not true for all systems, like something on fire, some kind of frictional system. Those just dissipate energy as heat. But if it's just something that's free falling and you neglect air resistance and stuff, then it's 1-to-1. Whatever the potential energy loses, the kinetic energy gains, and vice versa. And therefore, the total of the two is always the same. All right, so that's a little bit like conservation of momentum. All right, and so in this case, there's a formula that you can write down. It's simply this: the total energy E is equal to whatever the kinetic energy is plus whatever the potential energy is. And potential can change into kinetic. Kinetic can change into potential. And so they'll have different values, but they'll always add up to the same number. All right? So that's like with the collisions, we always have the same amount of momentum, but we just redistribute it into 4 objects or 5 objects instead of just one. All right? And it's the same thing here. Now, let's talk about energy levels in Earth's gravitational field. So here's some guy down in Mexico doing a flying body slam or something. I don't know. It's kind of a cool picture. It's one of my favorites. Perfect timing. Those 2 guys. Oh my God, there's a 3rd guy there. I hope he's not trying to do I don't even want to think about that 3rd guy with his feet up in the air. Oh my goodness. Anyway, let's talk about this. Mountain Dew. Okay, so you have a 2-liter bottle. That's about 2 kilograms. Mountain Dew. So let's just round it off to 2 kilograms. And we're going to bring it up 10 meters. So that's like maybe to the top of the ceiling here. That's maybe 10 meters. Yeah, maybe 10 meters, approximately. Maybe a little less. Anyways, so let's say, like to the top of the room. Now, mg delta y. Delta y is positive 10. So you better write this down because you have a clicker question coming up. Multiple choice. So delta y, you bring it up to 10 meters. Delta y is positive 10 meters. Okay. The mass is 2 kilograms. All right. 2-liter bottle. And g is good old negative 9.8 meters per second squared. And those 3 quantities, mg and h, 10 meters, those all multiply out to a joule, to joules. So the unit of work, the unit of energy. Okay. So here's a question for you. What is the GPE of a let's see if you guys have X-ray vision or not. All right, what is the GPE of a 2.0 liter bottle of Mountain Dew, 2.0 kilograms, at y equals 10.00 meters above the floor? All right, now some of you already saw this, but the rest of you guys that didn't see it, try to work it out. And those of you guys that saw the answer, try to work it out too, see if you know what you're doing. I can't do anything about you answering it, but you better make sure that you can do it, because this set of questions is going to be on your homework this weekend. You're going to have a little practice with this stuff. All right, so take a few minutes, a minute or so to do that. And while you're doing that, let me remind you that Miss Anna has off our illustrious TA, one of the finest of all time, in fact, is having office hours tomorrow from 1 to 3, 9 to 11. Fake out, little fake out. 9 to 11 in the physical sciences building, in the little pod or little alcove at the end of the hallway on the first floor. So you go in the main entrance, you go by the elevator, then you'll go by my office, then you go by a bunch more offices, and then down there, almost at the end of the corridor, is a little alcove where she will be. There's a marker board. You just work on problems and stuff. And hopefully by tomorrow, what is it now? 9 to 11, right? 9 to 11 tomorrow. Hopefully you'll have your homework ready to go, and you'll be able to work on it with Anna. So that's good. Okay, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Yeah, I guess everybody saw the answer, or either that or everybody's a genius because most of you got it. So that's good. So write that down. Let me ask you a question. This is not in, oh, by the way, here's the calculation. Okay, minus mg delta y, that's equal to negative times the mass, 2.00 kilograms, times good old g, negative 9.8 meters per second squared, and then times the delta y, which for us, it's positive 10 meters. Now, on the way back down, you're going to lose all that. But where does it go? Kinetic energy, 1/2 mv squared. So there's your calculation. Now, what you can do on your table like this, you can write down, okay, kinetic energy up there is 0 because it's you're holding it there, and it has potential energy of 196 joules. All right. Now, what does that tell you about the total energy, capital E, the total mechanical energy? Remember that equation I wrote for the total mechanical energy, E? What plus what? Right, kinetic energy plus potential. So that means that the total energy is 196. As a matter of fact, you can put ditto marks all the way down now for the energy. You know, in the energy column, the capital E column, it's 196. That's the part that's constant. As we move between, now the potential energy is not going to be the same. You know, so if we go down to, you know, like y equals 6 meters, we'd have to calculate potential energy again. And then we'd have to have a kinetic energy. That would start having a little bit of kinetic energy over in the kinetic energy. You know, the kinetic energy over here, it starts at zip zap because you're holding it. Then you drop it, and then 2 meters down, you're going to have some kinetic energy, and you're going to have a little bit less potential energy. And you can calculate the potential energy if you know the height and the mass every time, and so you can figure out everything about this table. Question? Right. For this object, starting at this elevation, E will always be the same. So you can calculate GPE and then kinetic energy and total energy at any level. Now, let's go down all the way down to the bottom, down to the floor level. All right. So just before impact, what's the kinetic energy going to be? Wait a minute. What's the potential energy going to be right before impact? When y is equal to 0. What's the potential energy going to be? 0. Oh, it's going to be 0. So what is the kinetic energy going to be? 196. All right. So those two numbers, and of course, the total energy is 196. They're going to be the same. So you can put ditto marks all the way down in the third column, the energy column. But notice, you know, the kinetic energy, the potential energy, they're changing. Those are the things that change when you're in some kind of a the gravitational field of the Earth. One way to think of it, and this is in terms of the idea of exchange, You're exchanging kinetic energy for altitude. Go ahead and write that sentence down. Exchanging kinetic energy for altitude. That's synonymous with saying exchanging kinetic energy with gravitational potential energy. All right? You're exchanging energies, but colloquially, you could think of it as exchanging energy for altitude. All right? Now, this is actually what you're going to see on your homework, something like this. A table with the Y in the first column, then GPEs, and then kinetic energies, and then total energies. And see here over here, in the far right column, that's your dittos. Because once you figure out the kinetic energy, like where, down here, or figure out the potential energy up here, that locks in this column all the way down. All right? Now, I didn't dismiss you yet. I've got 2 whole minutes. But this is where we dismiss. The next homework over the weekend, we'll have a bit of practice with this table and some other concepts. All right? You're dismissed now. If you want to come up and talk to me, it's fine. You turn